Hello there, welcome to another problem session. Today we're going to do some problem in Lensmaker's equation. So Lensmaker equation is is this formula for thin lens. What it is if I give you the radius of curvature of the two surfaces and give you the medium that the lens is surrounded in. So this medium is same as this medium on the two sides, and a refractive index of the lens. Then you can show that the focal length of the lens will be this. So the way this formula works is this radii can have a positive or negative value. So if like over here in this lens, we are assuming that the rays are coming from here, and so then the encounter, this surface is bulging out towards the ray. So that's how it's convex interface. Now the ray coming from here, this end is actually bulged in as far as the ray is concerned. So this will be concave. So over here, if you look at it, in this particular double, both of them will be convex, because when I come from this end, this is the ray, I encounter a bulge towards me, so this is convex. And when I'm here, I also encounter a bulge towards me, this is also convex. But over here, I encounter a kind of hollow kind of interface, and so this will be concave. But when I come here, I encounter bulge towards me, so this is convex. So when another can be a plane interface. In that case, the radius will be infinity. Doesn't matter plus or minus infinity, because 1 over r2 will be 0 here. Okay, so how do you use it, and why is it called Lensmaker's formula? So normally what you're going to have a problem is you want a lens of particular focal length. So suppose I want a focal length. So say one focal length equals to 25 centimeter. Okay, how do I make a lens out of? So this is a design problem. So this is a design problem. So if I want to design a biconvex lens, which will have, suppose I have an instrument which can carve out these spherical surfaces. So if I want to design a biconvex, say you want a biconvex, and so you need to pick up a material and a medium that will be, say you want to have a medium, N0 is 1, maybe air. This is vacuum or air. Okay, air is a little bit more than 1, but we can just use 1. And say material you pick is, say you pick a glass, so that's 1.5. So you already set these guys up. So now you have to choose R1, R2. And suppose I pick R2 is 20 centimeter. Okay. Then I can pick R1. So this was something I could do on my instrument or machine I have, where I can machine this at 20 centimeter. Then I'm going to figure out machine at what the other surface to machine at what interface. So we can just solve it here. So 1 over 25 will be 1.5 minus 1 over 1, and it's going to be 1 over R1. That's the one we want. 1 over 20. So I just solve it, and it will tell me what the R1 has to be, this surface has to be, and there has to be both, because I'm using plus, this is plus, so you can solve it for let's see, 1 over 25, so this is half times 2 plus 1 over 20 is 1 over r1, so this is going to be say 100, and so this is 8 plus 5, so r1 will be 100 over 13 centimeters. I hope I didn't make a mistake, but that's the way it will work if I have biconvex. But for some reason I wanted this kind of lens, one convex, one so suppose wanted this type of lens with f equals to 25 centimeter. So this is converging lens, so we don't want this will not work. So we want this kind of lens. This will also work, but say we want to this, and so n0 is also 1, say n1 nl equals 1.5, and say again I pick up r2, but this r2 has to be negative now. This will be a negative because it is a concave. When I come from here, this is a concave. R2 equals to minus 20 centimeter. Okay, so now what will be, so same problem will be 1.5 minus 1 over 1 over r1, r1 plus 1 over 20, and then you can solve for r1, and this r1 will be same way, 2 over 25, but this time it's going to be minus 1 over 20, and so it's going to be 8 minus 5 over 100 is equals 3 over 100, and so r1 will be 100 over 3. Okay, let's do another example. Another example you can do is, suppose I want this situation. We want a symmetric situation, maybe symmetric. So this r1 and this r2, they're equal to each other. Let's call it r in absolute value. So we want to find this, and I'm a lens maker. I've been said, give me a lens of focal length 25 centimeter, and I have n0 equals to 1, and nl material I have is 1.5 refractive index. So in this case, we will get what the r should be. Okay, what the absolute value of r should be. Well, we start from this incoming ray. So this is the r1, this is r2, right? And this is so this is going to be positive, and this is concave, this is negative. So I'm going to do 1 over 25, 1.5 minus 1 over 1, and then the first one is 1 over r minus 1 over minus r, because the second one is a concave. Concave because when you come in here, for this ray, this is bulging in, carved out. So this is 0.5, and this is 2 over r, which is 1 over r. So in this case, actually, the r you want is equal to the focal length you seek. How about if I'm given, we do another example. So this is example 3. Let's do a fourth example, which is kind of like this. I'm going to draw it out like this. So, and if I look at this, this radius is 10 centimeter, and this one maybe 15 centimeter. So what is the focal length of this? Well, let's say which way should I point? Well, actually it doesn't matter which way I point. So suppose this orientation versus, so this one will be 15 centimeter and this will be 10 centimeter. So which one of this orientation should I use? Actually it doesn't matter. You get the same focal length. Let's look at show it to you. So if I come in here, I have a bulging in, so this is a negative concave, and this one, when I come in, this is also negative. In this way, when I come in, this is actually positive because this is convex. When I come in here, this is convex also, so both positive. So it's kind of very crazy. If I have both negative and both positive, how come I'm getting the same focal length? You will get the same focal length, you will see. So 1 over f, and we can do NL equals to 1.5 and NO equals to 1 and NO equals to 1. We'll do the same thing. So 1.5 minus 1 over 1. And so this one is negative. First surface is 10 minus 1 over 10. So 1 over 10 with a minus here and 1 over minus 15. So this is 0.5, and so minus 1 over 10 plus 1 over 15 equals 0.5. 30 minus 3 plus 2. So this is equal to minus 1 over 60. So F equals to minus 60 centimeter, right? So this is actually diverging lengths. Using this, I get 1 over f is 1.5 minus 1 over 1. But the first, this is the R1 now, and this is R2 now. So R1 is 1 over 15 plus minus 1 over 10, which is the same as that. So this is 1 over 60 also. So F equals to minus 60 centimeter. So regardless of which way, you either use it facing this way or use this, you're going to have same focal length. Another thing that I really didn't overemphasize or emphasize at all is the thickness of this is considered to be close to 0. So these are thin lenses, okay? And you'll come up when we make a assumption to actually derive this formula. So let me just address a quick derivation of this formula. There is a lengthy derivation you can do, but I'll do a quick derivation. It's a quick and dirty, so there are a lot of things will remain unexplained, but it's instructive enough for me to do it, okay? Okay, so we want to do a quick derivation of this. So this is the first interface. We just call it R1, and this is R2. And this can be positive or negative. The sign will come later. Okay, so let's look at a particular example. I mean, this could have been like this. This could have been like that. This could have been plain, but all the cases are included in the sign. So we don't need to worry about the sign right now. Just look at a particular case like this. Okay. In this case, what's going to happen? For the interface, we can imagine the object is here, and this thing goes on forever. Then it's going to make an image over here, somewhere here. Image 1. So let's call it P and P1 for the interface 1, and this is Q1. Now these rays will continue and hit this interface. So this will become same as object for this interface. Object for this interface. And so let's look at the distance we're doing. This will be P1, and this will be Q1, and this will be P2, and maybe the image is formed over here, and this is Q2, and this distance will be Q2. So what we want is relationship between Q2 and P1 and N0, NL, R1, R2. So we want a relation like this, and we're going to find, this 1 over Q1, Q2. We're going to get 1 over P1 plus 1 over Q2 equals this 1 over F, using these guys when t equal to 0. I'm going to just set t equal to 0. So how do we do this? Okay, so we can do step by step. So over 1 over here, 1 over Q1, NL over Q1, because just this interface, just using that, we already derived this in the previous videos, that whenever you have a convex interface, it will be N0 over P1 equals to NL minus N0 over R1. This is a convex. When I go out there, this is concave. So we're going to do for the concave. I'm going to find out this becomes a plus. And now it's going to be NL over P2 plus N0 over Q2 equals N0 minus NL. This is the second one, this is the first one, and it's going to be minus R2, because this will be concave. We're doing a particular example just to be specific rather than completely generic. And we have P2 is T minus Q1. P2 equals T minus Q1. Right? So we are going to say T is 0. I'm going to set T equals 0 here. So P2 equals to minus Q2. Minus Q1. So if I put it over here, and so this is minus Q1. Now you can actually see how we can solve it for N0 over Q2 in terms of N0 per P1 and the rest of them. It's just, you could just add these guys, just add them. This will cancel this, and so you have a N0 over P1 plus N0 over Q1, Q2, the final image distance from the center of this lens, thin lens, is NL minus N0 1 over R1 plus 1 over minus R2. And this minus is coming because it's concave. So we have a 1 over P1 plus 1 over Q2 equals to NL minus N0 over N0, 1 over R1 plus 1 over minus R2. And So this is this. If you remember, 1 over p plus 1 over q equals 1 over f for thin lengths. So equating this on the right side gives me the desired formula. Okay, I'm going to stop here. This was a good instructive derivation. You can also derive this by not relying on these formulas. Instead, you could trace a horizontal ray. Where does it go? Over there. And how it ends up, maybe horizontal ray goes over there and then goes there. So that will be the focal length. So you can use a horizontal ray, and where the focal length ends up, you can trace the rays and follow the rays and use a small angle approximation to get that. But I'm not going to do that more lengthy derivation, because that derivation is actually already captured by these derivations, those steps of a small angle. Okay, if you like this kind of thing, you may want to check out this website. Tell your friends, like or share, so that more people can actually benefit from these explanations. Talk to you later. Bye.